So then you can rewrite this molecule, but what would happen if you rewrote all of this is basically you would see that this top molecule, that top benzene ring, okay, so we cleave that oxygen-carbon bond, so now the oxygen side, remember, the oxygen side, which is this side right here, that oxygen side got the addition of a hydrogen, right? So now I'm going to add my hydrogen to the oxygen side. And then everything else stayed the same. So that's why I'm not being super detailed with my structure. I'm just going to put blah, 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 R group, everything else is the same. What really matters is that I added on a hydrogen to the oxygen side. Right, so again, a hydrogen got added on to the oxygen side. And then, well, what happened to the alkyl group? Well, remember the carbon side, so that CH2CH3 didn't just disappear. That CH2CH3 is the carbon side, which should receive an OH. So really keep track of what I'm highlighting in yellow. So we already predicted that the oxygen side would get the addition of a hydrogen and the carbon side would get the addition of an OH group, right? And so for our carbon side, we added a hydrogen. And for our oxygen group, we added a hydrogen. That oxygen right here got a hydrogen. And this carbon got an OH. And what do we know about alcohols? What we talked about in our oxidation reaction? This alcohol can undergo two reactions, alcohol dehydrogenation followed by aldehyde dehydrogenation to get us all the way from the alcohol, which is the oxidation state right now, to the aldehyde, to the carboxylic acid, right? Like alcohol, aldehyde, or ketone, and then carboxylic acid. And so what ends up happening, you'll see in a lot of your answer keys when you're doing these practice problems, is this actually turns into the carboxylic acid. So you'll actually see CH3COOH as your carboxylic acid. So this CH3COOH came from this piece, the CH2CH3OH. Why? How do I know that? Well, there's two carbons, and then rather than having a CH2CH3, now I have this CH3 group is still there, but I have the COOH because we just underwent oxidation completely from the alcohol to the aldehyde all the way to the carboxylic acid. So instead of dwelling on the details, just think, okay, well, this cleavage, this CH2CH3, if we follow it, it turned into an alcohol first, that's CH2CH3, and then those two carbons then turned into that part of the carboxylic acid because oxidation occurred to that piece. So now we can think of that as kind of like a side reaction. So that happened, it's on the side. But the main thing that happened is that OC bond, carbon-oxygen bond was cleaved, and then we ended up with an OH right there. So this was going from here to here, phase 1, CYP450 mediated O dealkylation. But what did we create? We created an OH. And we already talked about how an OH can then undergo what? Phase 2 glucuronidation, right? So we already discussed that in the other pathway, the previous pathway. But I wanted to bring up something else, which is that aromatic hydroxylation, aromatic alcohols. Okay, this aromatic alcohol that we see, why is it an aromatic alcohol? Well, it's an OH attached to a benzene ring. So this aromatic alcohol right here, an OH that's attached to a benzene ring, this aromatic alcohol can undergo sulfate conjugation. Okay, so this phenol or aromatic alcohol, or phenol, can undergo another phase 2 reaction called sulfation. Okay, so I'm going to get rid of this phase 2 glucuronidation because we already saw an example of that. And now we see this OH, we can do sulfation, but not any OH. It has to be an aromatic OH. So when you see an aromatic OH or a phenyl, this molecule can undergo sulfate conjugation. So now I'm going to draw out the sulfate conjugation. All you'll do is you'll replace that oxygen. So I'm drawing the top part of the molecule again, O. All right, here, so instead of the hydrogen, I'm going to actually have a sulfate group, OSO3 minus, and then the rest of the molecule is going to be the same. And so again, I'm not being super picky with how I'm drawing this because I'm just showing that the OH got replaced with an SO3 minus, which is a phase 2 sulfation reaction. So this is phase 2. So now you can go to this list right here and you can add on some notes that sulfation happens when you have an aromatic OH group. And then also what we'll talk about in the next video is that naphthalene can undergo another phase 2 metabolism reaction based off of this COOH group. So go ahead and before you move on to the next video, see if you can figure out what phase 2 reaction can occur on this COOH based on lecture and your list of phase 2 reactions. Try to see what you think might happen to that COOH.